Hello everyone. Today we are going to talk about 2.5 exact equation. So we have equation here. So the form of equation we have, let me just read. We have form using any letters, right? So any variable and in terms of x and y. And we have dx plus any letter in terms of x and y, dy equal to 0. Then, if we divide by dx, both sides, not both sides, both, yeah, every term, right? Then we get dy over dx for this second term. Yeah, we can see that, right? Okay, then from this, again, the original equation, then we want to divide by dy at this time for every term. Yeah, then we get dx over dy. Yeah, so for instance, let's do that. This is equation. Yeah, then if we want to divide by dx for every term, then this will be simplified. Then we get dy over dx. Yeah. Okay. Then from the original equation, right? So there will be like this. Yeah. The original equation, we have 3x squared, y squared dx plus 2x to the third power y dy equal to 0, right? Okay, now we want to divide by dy every term. Then, oh, I forgot here. Yeah. Okay, so here dy over dy there, dy there, dy, right? Okay, then we simplify. So that's how they got here, dx over dy. All right? Okay, so what this mean? This mean we're looking at the equation and then we want to derivative with respect to x. Then this one, we're looking at the equation of x. Then we do derivative with respect to y. All right? Okay, now we have a theorem. So we just using any letter. So we have a function. So the function in terms of x and y, right, has a continuous. So I want to denote continuous CTS because too long letters. Partial derivative. So we learn how to do partial derivative in calculus of 3, right? So we are using partial derivative with respect to x. So we denote f sub x, yeah? Because this is a subscription, so we read f sub x. Then the notation like that, right? So df over dx. Looking at the f equation or function, then we do derivative with respect to x. Yeah. And we have f sub y. That means partial derivative with respect to y, right? So we denote this notation as well. Okay. Let me read that theorem. So we have a function or equation. So we are using the function better because it's a continuous function, right? So partial derivative exists in the continuous function, right? So like a derivative, right? Derivative exists when we had smooth function, right? Okay, now we have a continuous function and partial derivative. We can do that, yeah? Then partial derivative with respect to x, partial derivative with respect to y. Then the function equal to c. So c is the constant. So the function is c, then it's the correct? Implicit, right? Implicit solution of differential equation. Then form is the partial derivative with respect to x plus partial derivative with respect to y equal to 0. So we had implicit solution before, right? In general, we cannot express as y, right? So for example, we have too many y, yeah? So then we cannot solve for y. So, but then not all the time, right? So let me write down. So think x squared plus y squared equal to 1 better. Then we can solve for, this is implicit equation solution. Then we can express this one explicit, right? So y equal to plus minus 1 minus x squared, right? This is explicit. Solution. Yeah, we did that before. Yeah. All right. Now we have the question here. Let's take a look. So we have x to the fourth power, y to the third, and equal to c. Then it's an implicit solution of this continuous function, right? All right, so let's take a look. So let's take a look at theorem, right? So theorem, they say that the continuous function equal to c is a constant. So this is the one. It's an implicit solution of a differential equation. And that partial derivative exists for x and y equal to 0, right? Okay, let's just show that, right? All right, so we have the first term will be partial derivative with respect to x, and second will be partial derivative with respect to y, right? Okay, let us do this one. It's been a while, right? Okay, so let us do, can you see? Okay, hold on one second. Let me make it bigger. All right, so let the function f of x and y equal to x to the fourth power, y to the third plus x squared, y to the fifth plus 2xy, right? Okay, now we're looking at the function f and partial derivative with respect to x. Yeah, that means partial derivatives with respect to x. Okay, so that means we treat y as constant, right? Means treat y as constant. Okay, so this is a constant. This is a constant. This is a constant. Okay, let's do it. We do derivative x to the fourth power. So 4x to the third power, right? Y to the third power is constant, so we keep the constant, right? So let's do that. So 4 x to the third power, and then y to the third, right? Okay, second term, x squared, we want to derivative x squared, which is 2x. Yeah, 2x. And then y to the fifth power is constant. So we writing. Okay, now plus 2 is a real constant. So we keep that. And x, we want to derivative, which is 1, right? So 2 times 1 is 2. Then y is constant, so 2y. Make sense? Okay. Let us do partial derivative with respect to y. Okay, partial derivative respect y means treat x, no, sorry. Yeah, correct. Yeah. Yes, constant. All right. Um, let me rewrite this one. Okay. Okay, so this is a constant, this is a constant, this is a constant, right? Okay. Uh, the first term, looking at y, we want to derivative in terms of y, right? So y to the third power, so we derivative 3y to the second power. And then x is constant, we keep that constant, x to the fourth power, right? So 3, x to the fourth power, y to the second power, right? Okay, now, second term, we want to derivative y, so we get y, I'm sorry, 5y to the fourth power, x squared is constant, so we keep that. So 5 x to the second power, y to the fourth power, right? Okay, third term, uh, 2x, right? Because x is constant, so y is just by itself. So we do derivative, then we get 2x. Yeah. Okay. Let's check it out. Yeah. So this is partial derivative with respect to x. So we have this. It's the same, right? Okay, how about here? This is the form of partial derivative with respect to y, right? So can we get the same? Yes, we get the same, right? Okay, then we can say that this is implicit solution of partial derivative with respect to x, partial derivative with respect to y equal to 0. Yeah, because we check their answer here. Is it clear? Yeah. Okay, so let me copy everything. So thus conclude. Okay, next one. Oh, I don't need to show that, right? Hold on a second. Let me do that one more time. I need to show that. So maybe copy like that. Ah, okay. Uh, make let me just writing out. Yeah, let me pause and writing out. All right, so I wrote down everything. Okay, now, so we have an equation like earlier, right? And then we called exact like the this section title, exact equation, right? So the equation is exact if there is a function. So we are using function notation. So this is a equation notation, function notation. They're just using the first letter f from the function. Yeah. Such the partial derivative exists and then continuous. Yeah. Then that first term match with the partial derivative with respect to x, like what we did here, right? And the partial derivative with respect to y match with the second term, right? Then we called exact. So exact equation. All right. It's a terminology. So what's the exact means? If there is a function in terms of x and y, then we have a partial derivative exists in the continuous function, right? And then the partial derivative with respect to x agree with the equation of first term. It might be changed, right? Does not have to be first term. It can be second term, right? So anyway, the equation match with the partial derivative with that term, and then partial derivative with respect to y with another term. Okay? All right. Let us do example. So example of exact equation, right? So exact equation. So we have the function and this one dx, that one dy equal to 0, right? Okay. This is what we just did earlier, right? Then it matched, it agreed, partial derivative with respect to x, same as the equation of first term, and partial derivative with respect to y match with this another term equal to 0, right? So it was exact, right? Yeah, we did earlier. I mean, we did not use the terminology exact, right? So we just say that the partial derivative with respect to x equal to the equation of m of xy, and then partial derivative with respect to y, same as the equation of n of xy, right? Okay, now let's move on. Uh, okay, so I just wrote down the example. Is it exact? So we have 3x squared y squared dx plus 2x to the third power y dy equal to 0, right? Okay, so looks like this is a partial derivative with respect to x. And this one partial derivative with respect to y, right? Then how do we check exact, right? So we have to have a original equation, right? Okay, then how do you find original equation from derivative? Very good. Antiderivative, right? So let us do this. So antiderivative of 3x squared y squared dx. Okay, be careful. That means y is constant because we have dx, yeah? So constant. All right, then what do you get? So we add 1 to the power of x and then divide by a new power, right? And y squared is constant. So we keep that constant, right? And plus c, right? Okay, so we simplified and we have x to the third power y squared. Now let's check that. Let's check here too. So we have 2x to the third power y dy, right? So we have a dy, so x is constant, right? All right, so we do antiderivative constant, we keep that constant. 2 is the real constant, so we keep that 2. Then we do antiderivative with respect to y, so y to the second power over 2, right? Plus c. Then we will get, this is x to the third power, y to the second power. Okay, so look, it matched, right? So that will be original continuous function. So that will be f of x, y equal to x to the third, y to the second power, right? Like earlier, I'm going to show you that. Then we make a partial derivative with respect to x. Then 3x squared y squared here. And then we do partial derivative with respect to y. Then x to the third power 2y. Yeah? Make sense? Okay. So then what we can conclude is exact, right? Yeah, it is exact. Let me write down, writing out. Check of it. So partial derivative with respect to x, partial derivative with respect to y. Right? Okay, so, oh, I need a little bit space. Just a little bit high. Oh, it's a move on. It is a move, yeah. Okay. Those. It's exact since the equation equal to partial derivative with respect to x. The equation, which is partial derivative with respect to y, right? So that means that is equation. This is the equation. Yeah, make sense? And this is the equation of n x y. Yeah. Okay. Now we have a theorem here. So from previously, so we have exact, right? So theorem, the exactness is exactness. Condition, suppose M and R continuous. Oh, make a function, right? So we had an equation for made a function, right? So M and R continuous function and have continuous partial derivatives. So looks like my, but it's not. M sub y, right? And oh, I cannot erase. So M sub y means that with a partial derivative with respect to y, right? So we had n sub x. That means partial derivative with respect to x. Then we had the equation earlier, right? So this one we had when we use the function notation f of x, y, then that will be partial derivative with respect to x, right? Earlier, right? And this one, we had a partial derivative with respect to y, right? Okay, then they talked exact again. So we had exact then earlier. They are equal each other, right? And they are equal each other, right? Okay, now they say that partial derivative with respect x. So they are equal each other. In that case, partial derivative with respect to y. This one is partial derivative with respect to x. Yeah. Okay, let us do example so we understand that. Yeah. All right. So m sub y equal to n sub x. That means partial derivative with respect to y, partial derivative with respect to x. They are equal each other. Yeah. Okay. So we have an example here. All right. So let us do this one. By the theorem, we just want to show that, right? So the goal is we're looking at the function and so in that case, still we can use the equation, right? So we're looking at the m and then with the partial derivative with respect to y, then same as partial derivative with respect to x from the m equation, right? All right. Okay, let us do this. Okay, so we have the function, not function f. We don't have that. In that case, that's why we have to show this way as a exact, right? Okay, so we do partial derivative with respect to y. Okay, then let me writing out this one first. So we have m of xy equal to 6x squared, y squared, right? All right, then we do partial derivative with respect to y, then c is constant. constant. So we get 6, x squared constant, and then times 2y, right? So we get 12 x squared y. Yeah. Okay, now we have n x of y equal to 4x to the third power y dy. Y and y dx dy. Okay, now we're looking at the n equation and partial derivative with respect to x. Yeah. So that means y is constant, right? Okay, so yeah, normally I don't put the dx dy because equation does not include there. Because the form, right? So m dx plus n dy. That is the form, right? Okay, now uh, y is constant, so 4y times and 3x to the second power, right? So there will be 12 x squared y. Yeah? It matched, right? So it's exact. Since they agreed. Oops. All right. Okay, so let's try couple example. Uh, the goal, right? So goal. Next, yeah. All right, so we have the equation 3y cosine x plus 4x e to the x plus 2x to the second power. Okay, now we're looking at the equation and partial derivative with respect to y. So x is constant, so this is constant, and x is, that's a 2x. There is x and x, right? That's why this is a constant, this is a constant, and oh, this is also constant, this is also constant, right? Okay. Partial derivative with respect to y, we have a 3, right? And then cosine x is a constant, so 3 cosine x. And this is a constant, is 0, right? Everything is constant, 0. Everything is constant, is 0, right? So 0, 0 plus 0, which is 3 cosine x. Okay, now we're looking at the n. So we have n of xy, 3 sine x plus 3. Okay, now we're looking at n and partial derivative with respect to x. Okay, so there is no variable of y, so it's easier. So what's the derivative of sine x? Cosine x, right? So 3 cosine x. And we do derivative of 3, real constant is 0, right? So which is 3 cosine x. Okay, so it matched 3 cosine x and 3 cosine x, so it's exact, right? So thus it's exact. 6 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 cosine x. Yeah. Okay. So the last one for this kind of equation, right? So we have that. Okay, let us do this. All right, so m of xy equal to 3x squared y. All right, so partial derivative with respect to y. So constant. So we get 3x squared constant, and then y, derivative of y is the 1, right? Okay, now we have n for x to the third power, and then derivative with respect to x, and xy equal to 12 x to the second power, right? So they don't match. They don't agree, right? So it's not exact. Says, and so y is 3x squared. It's not same as n sub x, which is 12x squared, right? Is it clear? Okay, so slightly different with the previous theorem, right? So if we have original function f, then we want to know about the exact, then that from original function that matches with the partial derivative with respect to x, right? And then partial derivative with respect to y, right? This one, we don't have original function, right? And then we want to know about the exact, then look, even though we have the x, we are going to find the partial derivative with respect to y for this one, and partial derivative with respect to x from this one. They must be equal, right? Slightly different, right? Okay, so let us do this one. Oh, one more. Okay, so this will be last question for this section. Solve. We have equation equal to 0, right? So we knew, we knew this is m of xy, and then this one is n of xy, right? Okay, now solve means we have to find the original function, right? Original equation. Okay, so in that case, let's do the exact because we've been doing this, right? Okay, so let's find out exact first. So how do you find exact? We have only this form, then we need to show that, uh, check the exact. So we have to show that partial derivative with respect to y from the m equation equal to partial derivative with respect to x from the n equation, right? Okay, so we have m sub m of xy equal to 4x to the third y to the third plus 3x squared, right? Okay, so that would be this is a constant. This is a constant. Then we get 4 y x to the third power times the 3 y to the second power. And the second term is 0. So we get 12x to the third y to the second power. Okay, now what about partial derivative with respect to x? So let me write down n sub xy equal to 3x to the fourth power, y to the second power, 6y to the second power, and partial derivative with respect to x, so that will be constant, that will be constant, so that will be a constant 3 Then the partial derivative with respect to x, so there is a 4x to the third power, y squared constant, and constant is 0, right? So there will be 12x to the third power y squared. They are matched. So they are exact, right? So thus, it's exact since they are equal, right? 12x to the third y to the square. Now, why we need this? Because look, where's the theorem? Exact. So I want to show that. Oh, so equation note previously, right? Come on, copy, please. Copy. And yeah, so previously, right? So previously, so we have that, right? Okay, so now the partial derivative with respect to x is same as that m equation, right? And partial derivative with respect to y is the same as n equation, right? Okay, so there will be, let me, how do I say? So yeah, and thus, let me just conclude like that. So m of x, y equal to the partial derivative with respect to x, which is the equation 4x to the third power, y to the third power, this one, right? Yeah, so let me write out. So there will be 4x to the third, y to the third plus 3x squared, right? How about n, same as the partial derivative with respect y. There will be this one, right? So let me write out. Okay, so there will be 4y squared plus 6y squared, right? Okay, now, if this is exact, we already show that, right? But then, if we have this one, we can find the original function easily, right? Yeah, because just we do antiderivative, right? Respect to x, respect to y, like what we did earlier, right? Okay, so let me just using my way because book is a little bit confusing. So how do you find the original function f? We make an antiderivative respect to x, respect to y, right? That's it, like earlier, right? Okay, so let us do that. So we have antiderivative of 4x to the third power, y to the third plus 3x squared dx. That will be, what do you get? Y is constant in the case. Okay, so then 4x to the fourth power over 4, y is constant, y to the third power plus 3x to the third power over 3, right? Okay, good. Now we do partial, no, I'm sorry, antiderivative, antiderivative 3, ooh, 3x to the fourth power y squared plus 6y squared dy, right? Okay. Now, y, right? So this is a constant, x is a constant. All right, so antiderivative, what do you get? 3x to the fourth power constant, and then we do antiderivative respect to y, so y to the third power over 3 plus 6 y to the second power, so y to the third power over 3, right? Okay, now let's simplify. So we have a x to the fourth power y to the third plus x to the third, right? This one, 3x to the, oh, sorry, x to the fourth power y to the third plus 2y to the third, right? Okay, so we don't write out everything because we have this is the same, right? So we will use f of x y equal to x to the fourth power y to the third plus just one time looking at the previous note, right? So normally they match, right? So we have x to the fourth, y to the third. That's it. But then in that case, we have x to the third power and then 2y to the third power, right? So we are writing out. So x to the third plus 2y to the third, right? Okay, so let's check that. Check it out. All right, so uh, partial derivative with respect to x. Okay, x, 4x to the third, y to the third, plus 3x to the second. Yeah, match? Yes, right? How about partial derivative with respect to y? And looking at the original one again, so x to the fourth power, 3y to the second power, plus 0, and then 6y to the second power. Is it match? This one with this one? Yes, right? So this one must be original function, anti-derivative, yeah? Okay, now, we're not done yet. So we say that, look, oh, hold on 1 second. So let me write down the beginning, let me bring up the beginning one, the statement. So hold on 1 second. Uh, the beginning we have constant. Yeah, so look, we have whatever we said, and then I want to mention that the original function equal to c, which is c is constant, is implicit solution of differential equation, and they are equal to 0, right? Okay, so let us make that. Let us make the original function equal to c is an implicit solution of that equation. Yeah, so uh, we had copy. Uh, oops. We had earlier is yeah. Okay, so we say that f of x, y equal to x to the fourth power, y to the third power, plus x to the third plus 2y to the third equal to c. Yeah, c is an implicit solution. Yeah. So then we can say that is a implicit solution of the differential equation, this one, right? So we knew the partial derivative with respect to x. This is the same as, yeah, I can just writing out. I can see that right there. So for x to the third, y to the third plus 3x squared dx, right? Plus x to the fourth, 3y to the, okay, let me arrange a little bit. 3x to the fourth power, y to the second power plus 6y squared dy, right? Equal to 0, right? No. Oops, dy equal to 0. Yeah. All right. Now, we say that this is implicit solution, right? Then, explicit solution, we need to solve for y, right? If we can. Some, we cannot, right? All right. Let's make that. We have this one. X to the 4, y third plus x third plus 2y to the third equal to c, right? And solve for y. So let's move to the x to the third other side. So there will be x to the fourth, y to the third power plus 2y to the third equal to c minus x to the third, right? C is a constant, right? Constant. All right. Then y to the third is the common in that case. So y to the third, factor out x to the fourth minus 2 equal to c minus x to the third. And then we do divide, right? So y to the third equal to c minus x to the third over x to the 4 minus 2. Okay, now we make take the square root. Ooh, square, not square, cube root, right? Cube root to both sides to solve for y, right? So there will be y equal to c minus x to the third over x to the fourth power minus 2 to the 1/3. We call this is explicit, right? Solution. This one, orange color one, is implicit solution, right? Okay. Solution of, yeah, I don't have to write out, right? Yeah. Okay. Um, thank you for watching. I will see you in the next video. Bye.